Today we're going to be looking at set notation for VCE maths methods, but before we get started, you have to understand that set notation is used to describe the domain of a function. And to fully understand how to use set notation, first you have to understand what the different symbols mean. So first we have the curly brackets, which refers to a set of values. So for example, you could be given a set of values through this description. You can say my domain consists of this set of values is 1, 2, 3, 5, 6. And these are the different sets of values, as you can see. So several different numbers enclosed with curly brackets is a set of values. Then you have the hard bracket symbol, which refers to the endpoints of the domain being included. This can also be visualized on a number line, which I'll explain later, with a closed heart circle like that, which means it's included. So if you look at a number line from here to here, you could be given a set of values. So from 0 to 3. So we'll call this 0, 1, 2, 3. And to represent this, because there's enclosed by two hard brackets, there's two hard circles, closed heart circles. And that's what that would look like. So your domain is between 0 and 3, including those. Then we have rounded brackets, which means your endpoints are excluded. So if we did the same thing, but we had a rounded bracket on the 0 and a hard bracket on the 3, a number line would look like this. So say this is 0, 1, 2, 3. We'd have a closed heart circle here. However, excluding is used with an open heart circle again. So that's what that would look like. This E symbol, it refers to belongs to or an element of, which means you can represent this in questions. It'll come across as X belongs to this set of values. So 0 to 3, you could say. This is what X could be. X could be the numbers 0, 1, 2, 3, and anything in between those. Then we have an N looking symbol, which refers to an intersection. And you can see this on a Venn diagram as looking at two different sets of values, and you want the overlap between them. So you're looking for the section with the values that are in common. For union, this refers to OR. So it can be this set A or set B, but it can be both. So the OR is really important. That means that any numbers which are within both of these sets are included. Then we have subset. So this refers to a set of values being within a greater set. So this small internal circle refers to the subset. Subset or equal to refers to anything within the greater set, the larger set, the outer set. Anything in here, either the subset or the entire set. Excluding refers to having a set of values, but you don't want to include specific values. So you can have, again, your domain 0 to 3, but you want to exclude and cover with curly brackets the value 2. So on a Venn diagram, on a number line, it would look like 0, 1, 2, 3. An open heart circle because you're excluding it. Closed heart circles on the ends because they're included. So this refers to the integer 2 being not included in our set of values. Real numbers refer to all numbers real numbers are all numbers except complex numbers. However, those are not in maths methods, so you don't need to worry. So real numbers are all numbers. So root 2, 1, 7, 3.5, all numbers. R plus refers to positive real numbers, so this does not include 0. So we're looking at the set of not 0 to positive infinity. That's because 0 is neither positive nor negative. And again, with negative real numbers, you're looking at negative infinity to 0, but excluding 0. Integers refer to whole numbers, so they can be positive or negative, but they're whole numbers. And the n refers to natural numbers. So these are numbers which occur in the real world. So these are positive whole numbers. Because you cannot have 0 of something because it doesn't exist in the real world. You have to have at least 1, 2, 3, 4, 5. You can't have half of something. It just becomes a smaller portion of what it is, but it's still a whole. So now that we understand the different symbols and what they mean, we can move on to some application questions. So here we can see that we've represented sets of values with curly brackets. So what we want to do for part A is look at the intersection between A and B. So we're looking at the overlap between the two sets of values. So if we drew assigned A to the left circle, B to the right, we can see that what we have in common when looking at the sets is the values 1, 3, 5, and 9. So you would say 1, 3, 5, and 9 exist here. 4, 6, and 8 exist here, and no numbers exist outside for B. That's based on pulling numbers into where they belong, such as that. Now, from that, we can conclude that A and B equals the set of values 1, 3, 5, and 9. Then, as we move on, we have B or C. So if we assign this circle on the left to B and on the right C, it refers to all numbers within the sets B or C. So if we come back up to the top and we see the two sets B or C, first the set B is 1, 3, 5, and 9. C is 2, 4, 6, and 8. They have no values in common, but because it's OR, we're including everything in the circles, both circles. So that equals the set 1, 2, 3, 4, 5, 6, 8, and 9. Now, as we go across, you might come across several combinations of symbols. So this is A and B or C. In this situation, you would take a BODMAS approach and you go from left-hand side to right-hand side. So first, you look at A and B, and then or C. So, for this case, I have a poorly drawn Venn diagram, so we're going to ignore it, because I didn't prepare that far. And we're going to look at it as a combination of all three. Actually, we'll take it one step at a time. So first we find A and B, which from part A, we know that A and B equals a set of values 1, 3, 5, and 9. And then or C means we include all of the values from the subset of C. So then we can see that A and B or C equals the subset 1, 2, 3, 4, 5, 8, and 9. We've combined the A and B, and we've also combined the subset of C. And that's how you would approach those questions. Then we move on to looking at what would come up more in VCE Maths Methods exams when you're looking for domain and range. Well, domain, because we're looking at X. So we can see that there are two different ways to write this notation. We have our hard brackets excluding. Oh, that shouldn't have an excluding there. Doesn't matter. So what we'll see is this is one way to write it with hard brackets excluding this set of values. Or we can see it as these curly brackets with X as the variable we're focusing on and an interval of 0 to 4. So this does not equal that. However, it does refer to a portion of it. So it's similar to saying X belongs to 0 to 4 with hard brackets due to the including there. So if we look at this initial one on the number line, we're going to focus on the one I circle. This one just here, focusing on this one. We can see on our number line that if we start from 0, 1, 2, 3, 4, we have two hard brackets. So we're including with closed heart circles, but we have an excluding of the value 1. So there's an open heart circle there, and you just connect them. And that's what that would look like on a number line. Then as we move down, we have another set, but this time we have an intersection. So when we're looking for the domain for an intersection, you initially draw the two sets as separate ones. So we'll start at -2, -1, 0, 1, 2, 3, 4, 5, and we'll go to -4 as well. Now, this first set will be demonstrated through the green color. So we have an excluding -2 all the way to including 3. And then we have an including -4 all the way to an including 5. Now, because we have an and, we're referring to the overlap between the two. This means that we want to look at this section here where they have common values. So from that, we can deduce that x can belong to excluding -2 due to the open heart circle all the way to 3 including, because that's the overlap. Now, we have a union or an OR. So this refers to all values being included, and it doesn't have to be restricted by an overlap. So this is the direction of -infinity. This is the direction of +infinity. And so we'll go from 0, 1, 2, 3, 4. Get the gist. -1, -2, 3. And continuing on. So what we realize is, first we'll look at the left-hand side. We have a -1 including, so there's a closed heart circle, and this travels that was really bad. And this travels all the way in that direction. And then we'll notice for the right-hand set of values, we have an excluding 3 all the way in the +infinity direction. So that's what the domain is for this graph. It's everywhere except for this empty space. You can also write this as being all real numbers excluding -1 to 3. That is an alternative way to write this. Now, we've seen this through visual Venn diagram form. We've seen this on a number line. Now we'll look at it in a graph format. So what you want to do is, this is the typical application you'll get in your exams. So we're being asked to draw the graph of x² + 1, where the domain is including 3, that's a negative, including -3 to 2 excluding. So if we draw this graph, we can see the basic graph from the function with no restrictions being considered is this. This is x² + 1 with an intersection at 0, 1. But now we need to consider the domain. So we're saying that if we go from -3, -2, -1, 1, 2, 3, what we're looking at is an excluding here and an including here. So you can see we can relate this to a number line, because as you can see, this looks like our common number line. However, now we're looking at the graph. So what you want to do is trace up to the graph, and you can see that we're excluding here because the value x equals 2 does not exist based on our domain. And we're including 3. And all you have to do is connect the lines. And then we can see that this is what our graph will look like. Yeah, and then to understand what these coordinate points are, you'll substitute the x values in. So if you had f of 2, it would equal 4 plus 1, which equals 5. So this open heart point is 2 and 5. And then we look over here to the left-hand side, and if we had f of minus 3, that equals 9 plus 1, which equals 10. So our coordinates here are minus 3 and 10. And that's how you would apply the use of domain and interval notation to a graphing question.